It's me again, and I am live. As I said I'll be live, so now I am live for Strength and Six. That is what I'm live for, Strength and Six. I said I'll be live. And guess what? I am indeed. All right, we're busy with, let me first change the camera. We were busy. We were busy with this. We're busy with this. So now I'm finishing it up. So the next question says the number of coils in each spring. So if you want the number of coils, remember we already have D, so now we'll be able to find capital letter D, which is just 10 small letter d, and then that will help us get N. Remember this formula sheet. So this is the formula sheet we said we will talk about it. Yeah, this is the formula sheet. So we said we'll finish it up. So since we are finishing it up, this is the formula sheet, and now we can use, since we are looking for N, we can check. Oops, sorry about that. So we can check this one right here for X, because we do have W, we have D, we also have G, we have small letter D, we have capital letter D, we have X, so we just need N, so we can use that one. Okay, so we have W D cubed N over G, then D4. Then now we can make N the substitute of the formula. Remember we just used this formula to find capital letter D. So now we have capital letter D, we have W, because we got W from there. Then we have G was given. We have small letter d, we just calculated small letter d here. So we have everything, by the way. So now we can just go ahead and make N the subject of the formula, because we do have X. X was the first that we had to look for. So therefore N will equal Okay, this and that will come and multiply. So it will be x g d to the power 4. Okay, someone said I should play some music. Okay, it's fine. I don't have music at the moment. Then d to the power 3. Then that's it. Then you just substitute and get the answer. Then the last one for spring, so that you can move to Morse circle. The last one for spring, then it was that length, the one that I said that is definitely a new formula. They are talking about the solid length. They're saying the length of a fully compressed spring if it has two inactive coils. So that is a solid length. So that solid length will have D into, then it will be that N plus 2. 2 is for the inactive coils. Then you'll get your answer. Now I'm done with this example, but let me just go through it once again. We had this data to work with. Then we had to find X. Remember, the network was so bad during that time, so we had to find X. So that was X. What did we use? We used the formula for energy, for work done, strain. This is a strain energy. Yes, it's energy. Strain energy. Then that was the formula for it. Then after that, we got xt. We multiplied by 2. Then we divide by 15k. Then you get the answer for xt. That's number one. Then the second question, it was the diameter of the spring wire by using Wahl's factor. So if we're using Wahl's factor, that is why we have to calculate this kW, because that is Wahl's factor. Then we get the answer. Then after that, we are going to find strain, shear stress. We have Wahl's factor, but we do not have W. So we need that W first. So what we're gonna do, we already have the total energy. So we can use the formula for total energy. Then we just made W the subject of the formula. That's why we have this 2 UT over XT. Then now we can find WT. Then after finding WT, since we just want for the wire of each spring, so that means we need the weight for each spring. That is why we came here, now to get the load that is on each spring. We divided that WT by the number of springs, so that we can know each spring is carrying how much load. Okay, then we got the load for each spring here. Then after that, we have moved to now the stress. Then remember, we do not have D. So since we do not have D, we had to equate D to 10 small letter d. Remember, C is equal to 10. So that is why we equated it to that. Then we have our answer now. 10d times 8, that will be 80d small letter, then it will cancel 1d here. That is why you have d squared here. Then you make that d squared the subject of the formula. Since it's a square, you root both sides, then you are left with this. Then that's how you'll find your d. Then after that, now we are looking for, because the question is asking us to find the length, the number of coils in each spring. Then we can find now the capital letter D. Then after that, we will be able to finish up with the X, use the formula for X so that we can find the number of those springs. I mean the number of coils in each spring. Then there we have it. Then lastly, we are asked to find out the length of the fully compressed. We're talking about the fully compressed, that is the solid length. That's why we have LS for solid length if it has 2 inactive coils. So there you go, you have it. That's it. Now we are moving to Morse cycle, this last section, so that we'll just do that one. I will rush through it because it's at night as well, so I will rush through it. I'm not gonna stay long. I will rush through it. Okay, Mike Fester. So for Morse cycle, I'm just thinking, okay, because we already have our list of problems that we will be dealing with. So for example, we're starting from 124 on our pamphlet, 124. It goes from 124 till I think 129. Yes, 128 actually. 124 the way to 128. So I'll start with 124. They are saying the in-plane stress on an element are shown below. Okay, the in-plane stresses on an element are shown in plane below. Okay, let me just quickly draw that. So we have that as 10 megapascals. Then we have this as 50 megapascals. But this one is mostly the N5 star type because you are just drawing. Then you have shear stress in that direction. They are saying that shear stress is 40 megapascals. So if it is 40, remember we said that when a stress, this shear stress, if it causes this element to rotate anticlockwise in this direction, in other words, that means it is positive. So this shear stress is on the X face. So in other words, this is stress X. That's on the X face. Then this one is stress Y, is on the Y face. So on the X face, the stress is positive because it's going in that direction. It is causing the element to rotate anti-clockwise. Now on the Y face, which is this face, on the Y face, it is rotating anti-clockwise, meaning that it will be negative. So you have to put these values. So you have X, you have Y. So for X, you will have, number one, is tensile. If it's tensile, that means it's compressive. So it's tensile, which means it's positive. So we'll have 50, then we'll have positive. That is positive 40. That's what we have. Then for Y face, we have compressive. Compressive is negative. So we have negative 10. And then we have the shear stress also being negative because it is rotating clockwise. So it will be 40. Remember, for this one, they are the same. They are always the same, but the only difference, it will be the sign for shear stress. So here we have the principal, the normal stress on this side. Then on this side, we have the shear stress. This is how you plot it. Then now we are going to plot it. Then let's read the question. The question says, construct Morse cycle for the element shown. Determine the maximum shear stress as well as the principal stresses and planes from the diagram. use the scale. Okay, they're telling you the scale. I'm not going to use the scale at the moment. I'm just going to show you roughly how it will look. I want to be fast because we need to sleep. This is what we have. Okay, so on this side, remember, this is for normal stress. Then on this side, this is for shear stress. Then we will take this first. So we have 50 and 40. Now, of course, we are told that we should use a scale, so you can mark. So we have 50. Okay. Maybe let me just do it like that. So let's say 1, 2, 3, 4, 5. There is 50. Okay, it doesn't really matter. It doesn't really matter how you count it. So let's say that is the 50. That's the 50 that we have. Then this 50 should go with 40. Okay, if I'm saying this is 10, 20, 30, 40, so that one will be 50, and so on. Then if this is 50, then on the other side we have 40, so we can have something like that. So that is the 40 on the shear stress. Then the upper side, it will be the negative values, negative 40. Then that is the 10, 20, negative 10, negative 20. Then we can join those two. We can also join these two. So basically, this is what we will be having. Then when you join these two, remember I said that positive is on this side for shear stress, positive is on this side for the normal stress. So now you join these two and then you try to draw a circle through them. Yeah, they'll form whatever circle. Okay, before you draw that circle, you must find a center place. How do you find a center? You just take a ruler. You draw a line between these two. Today I don't really have much equipment, so I'm just taking anything that is close by. You just join those two. Then that will be the center. Then you can try and look for the center. Where is it? To me, it's quite close to 20, but if I can add 10 and 50, that will be 60 divided by 2, that is 30. So basically, okay, let me say 50 minus 10, that's 40 divided by 2, that is 20. So we'll have 20. Let's say that is 20. That's where they meet. They are meeting at 20. Say this 20, that is where we will be having the maximum stress, because they said determine the maximum shear stress. So now we can determine the maximum shear stress right here. You will just measure this line. So let's say it is close to 50. Maybe let's say just say that is 50. Then it is minus 50 on top, because that's how it is. So to measure from there to there, it is 50. So we can say now the maximum shear is equal to 50 megapascals. Then the second one that they asked for they said as well as principal stresses. What are principal stresses? Now, principal stresses, okay, so here it will be 20 and 50. Then there it will be 20 and minus 50. Now, for you to get the maximum shear stress, you must have a mean value for the normal stresses. So that is why the normal stresses will be the same. Here, remember we had 50 and 40. Here it was 50 and 40. But here we had negative 10 and negative 40. So that was negative 10 and negative 40. So that's what we had. Now here we have 20 and 50. This is the maximum shear stress. So the maximum shear stress, there it is, it is that value. Then when we want the second part, which is the principal stresses, the principal stress, it will be the stress where the shear stress is equal to 0. Now the shear stress is 0 in this line. Anywhere in this line, the shear stress is 0. So these values that you are going to get, of course, this one will be more than 10. I'm not sure which value. This one will be more than 50. I'm not sure which value, but it will be some value somewhere there. So since we will have that, you can just measure those ones and get the answer. So that is how you get them. You just measure those points where it is touching this line. That's where we get the principal values. So this principal value, it will be stress 1 because it's big. This principal value will be stress 2 because it is small. That's how you'll get it. So you can say stress 1 is equal to, you write the value, then stress 2 is equal. Now, when you are measuring these stresses, you always start from this line. This O, that's 0. You'll measure from this 0 to that place. Let's say that is A, and then this will be B. So you can say OA is the value for this. So you have stress 1 is equal to OA. Then you'll write it in, when you measure it from there to there, you'll get the value. Then what about stress 2? Stress 2, again, you measure it from O till B. So it will be OB. That will be the value for stress 2. So in this case, that's how you would do it. Okay, this is just a rough work. The next question says, sketch the element in the transformed position to indicate the angle of the principal plane. Now, remember we said that the principal plane or the principal stresses are in this line. This is the plane. So this is the principal plane. In the principal plane, the shear stress is equal to 0. So meaning that there won't be any shear stress when we are drawing this element in this plane. But how are we going to draw it? We must first measure this angle. And we know that this angle is equal to 2 theta. That means whatever value you are getting in this angle, you have to divide by 2, whatever value. So you measure this angle. Let's say this angle is 40, for example. If this angle is 40, then you are going to measure 20. So you'll measure 20 from here. So this angle should be 20 if that one is 40. If this is 40, this should be 20. Then you are going to construct that element, but this time you are going to construct it in a rotated form. So it will look like this. Now this principal stress is stress Y. So stress Y it is negative, meaning it is compressive. So it's still compressive. That is stress Y, and it's equal to whatever value, which is OB. Then we have this other stress. This one, it will be stress 1 over stress A, stress X. And it is on the positive side, meaning that it is tensile. So this stress will equal that one, stress 1. So this is stress 2, this will equal stress 1. That is how you draw it when it is transformed in its transformed position. And you'll notice that I did not draw these lines. I did not draw them. Why? Because remember, these are principal stresses. When we talk about principal stresses, the shear stress is equal to 0. That is why I did not draw them. The stress is equal to 0, the shear stress right there. Okay? I think that makes sense. So you will write that as theta. Maybe say theta is equal to 20. I'm just making an example. I don't know because I didn't measure that. But I said, if this is equal to 40, then this must be 20. All right, that is how you draw Morse circle. That's example number 1. I'll do one more example. This time I will include calculations as well, okay? If you have any questions, you can ask them. All right, now let's go and try 125. So 125 says an oblique plane is shown in the image below. Okay, let me page over because this is Morse circle. I don't want to confuse. Okay, if there are any questions, you can write your question. If you have any question, you can write it. If you have any question, you can write it. Okay, I hope there's no question. So let's go on and do the next one. An oblique plane. Okay, we are given this oblique plane. So then after that, they're showing that it's an oblique plane by writing that 30 degrees. Then they're telling us is equal to 75 MPa. Then in this case, both stresses are tensile. Then this one, stress Y is equal to 45. So if both are tensile, that means they are both positive, right? Then they are saying we have this for shear. So that is 25 MPa. Now, the first thing that you are going to do is to get the X and Y coordinates, right? So for X coordinates, I will have 75. This 75 is tensile. This 75 is tensile. If it's tensile, that means it's positive. So I'll write 75, that is positive. Then when we come to the shear, we look at the X face. The X face, the shear is causing this member to rotate clockwise. If it's rotating clockwise, it's negative. So I'll have negative 25. Then I have the Y part. For the Y part, it's tensile, so meaning it's positive 45. Now it is going in the direction. So in that direction, it is rotating anti-clockwise, which is positive 25. So I said one must be negative, one must be positive for the shear stress. Okay, that's it. Then let's go ahead and read further the question. Remember, this one is rated by 30. It is a rotation of 30. So we know that theta is equal to 30 degrees. All right, so let's go ahead and read the question. It says, prove from the image above that the sum of the normal stresses is equal to the sum of direct stresses acting on the plane. Meaning, then they also wrote it, they're saying, meaning that stress x prime plus stress y prime is equal to stress x plus stress y. So they want us to prove this. So how are we going to prove it? We have to definitely calculate these values first, because we already have these ones as 75 and 45. So now we need to calculate the rotated stuff or the transformed values. So let's go ahead and calculate the transformed values. How are we going to calculate them? We will go to the formula sheet. So when you reach the formula sheet, this is what you have. Okay, let me put it like this. This is what you have. That is, okay, let me use this. This is the one you're going to use for x. I'm sure let me make it a little bit bigger. Yeah, this is for x. So for the transformed x, this is the formula for it. Then obviously for the transformed y, this will be the formula for it. That is the transformed y. So we are going to use these formulas. So let's go ahead and use them. Let's start with x. It's quite a long formula, but in reality, it is quite simple. But let me first write it down. So it says it's equal to stress x plus stress y over 2 plus stress x minus stress y over 2 times cos 2 theta plus xy sine 2 theta. Now, here we just substitute as it is. There is nothing fancy we are going to do. We are just substituting, that's all. So we'll substitute in these values. You have, remember, you have these stresses there, they are there. So you just do the substitution. So in the place of stress x is 75, you just put 75 plus 45, because that hand side 45 divided by 2 plus, this plus is from the formula. Then again you write the same values, 75, this time is minus 45 over 2, then times cos 2 theta. Remember, theta is equal to 30. So when you're saying 2 theta, that means that is 60. Okay, now is this theta positive or negative? All right, let's look at this line. How do you know it's positive or negative? This line, if I'm from the x face, I am going in this direction. So I'm going in this direction. I'm going in the positive direction. So this is the positive angle. So that means this 30 is positive. So that 60 will be positive. Okay, that's how you look at it. Okay, so that is 60. Then you have plus this in your calculator, you get the answer. Okay, then you come and now go stress y prime. Remember, if you have a question, do not hesitate to ask. You can ask your questions. If you have okay, now you still have the same formula, but now you change the sign. You will have negative here, you'll have negative there. That's what we have, negative and negative. Okay, so that is x plus stress y over 2 minus x minus stress y over 2 cos 2 theta. 2 theta is still that, okay, cos 2 theta minus, again you have minus, substitute minus there, xy sine 2 theta. Then again you just substitute those values. Now you put negative in those places. Okay, so you'll have 75 plus 45 over 2 minus 75 minus 45 over 2 times cos 60 minus 25 sine 60. Then you press all of that in your calculator, you get an answer. Then after getting that answer, you'll substitute those values. Remember, on this side, you have 75 and 45. So you know that we'll go back to that formula. Stress S prime plus stress Y prime is equal to stress X plus stress Y. Now stress X is 75, stress Y is 45. You're gonna add them up. So 5 and 5 of course is 0. 7 plus 5 and 5 is 10, which is 0. 7, and we have 1 there. 7 plus 5, that is going to give you 12. So that means we have 120 on this side. Also on this side, these answers, when you add them, they should give you 120. That's what it means. So when you add this answer, the answer that you are going to get here, and the answer that you got there, when you add them, they should give you this 120. That's what it means. And then you're done. You have proved. Then after that, they're saying calculate the resultant stresses. Now, when you're calculating the resultant stresses, again, you come to these formulas. Number one, you look, remember, these are the rated values. So now you'll come and find the one for the shear stress. So the transformed formula for shear stress is this one. Can you see? Now it's shear stress x prime and y prime. Since we are dealing with x prime here and also y prime, so even here for shear stress, we should use those prime values, x prime and y prime. So we're gonna use this formula, in other words, to find this value. Then that's the one we are going to use to is the resultant. Okay, we do not have the formula for resultant here. Ne? Okay, there is none. All right, I'll show you the formula for resultant. It's fine. I can see that it's not in the formula sheet, but it's still fine. So this is number one. So now we're moving to number two. Then this number two, we will first calculate that shear stress. So shear stress X prime Y prime will equal, you just put that value. It starts with a negative. So stress X minus stress Y over 2 times sine 2 theta minus, then here it will just be cos 2 theta. So remember, this is 2 times 30, that means it is 60. 2 times 30, that is 60 degrees. This one, remember, it was 25. Then this one, it was 75. This is 45. So that's what you have. You just put those values, you get the answer. That's how we solve this problem. After getting that answer for the rotated shear, it will always the resultant. This is the formula we're going to use to calculate the resultant stresses. This is the formula we're going to use to calculate the resultant stresses. I know it's not in the formula sheet, I just checked for it. I didn't see it here. Since it's not here, what you are going to do, you're going to use this to calculate the resultant stresses. So this is the formula we're going to use. You can also write it down. So this answer obviously is that one, that one, that answer. That's it. That's what you do when you are calculating for the resultant stress. Any questions? Are there any questions? Let me just again go through this example one more time, just to explain what I did for the last time. I said that we have this element. The thing that I think many people can miss, it is the rotation of that angle. How do we check if this angle is positive or negative? This is the X face. So on this X face, you move to the, you can see that you are moving in this direction. So if you're moving from the X face, you are following this arrow, you are going towards this line, you are rotating anti-clockwise. When you are rotating anti-clockwise, that is a positive angle. So when you rotate in an anti-clockwise direction, it is the positive angle. So that is why this 30 is positive. If that 30 was standing like that, and then they do this, then that means that 30 will be negative. We'll write negative here. Okay, so in this case, that 30 is positive, so it's a positive angle. So this is why I am putting 60 here, not minus 60. Even here, I'm putting 60, positive 60, because this is a positive angle. All right? Then when you come in this place, they have to be the same. If these answers are not the same, if these answers are not if these answers are not the same, that means one of these is incorrect. So they have to be the same for it to be. Yeah, you'll catch up. But let's explain again. I said that, let me do one more example, one last example, because I thought that this is the last example, but now since you are saying you just arrived, so let me just do one more example so that I can clarify the question. But let me first explain this one. We have this angle is positive when it is rotating in this direction. It is positive because it is going in an anti-clockwise direction. So that is why it is positive. That 30 is positive. We are using formulas. Remember, this formula is stress X prime. It has to be primed. Now that means it's a transformed value. So when we transform it, we use the formula for prime, because the question said we should prove that this is equal to this. So that means we must calculate the prime values for x, the prime for y, so that we can ensure if they are the same. That's what we did here. And then we got those answers, two different answers. We said that when we add them up, they should give us 120 because these two, when we add them up, they are giving us 120. Then the second question said that we should calculate the resultant stress. So for a resultant stress, this is the formula for resultant stress. So we already calculated this there. That is stress x prime. So we already calculated it here. So now we were going to do this one. We do not have this. So we had to first go to the formula sheet and calculate this. So this is the formula for it. As you can see, start with a negative and show that you are noting that it starts with a negative, then x, stress x minus stress y over 2 times sine 2 theta minus shear stress xy times cos 2 theta. So I said 2 theta is equal to 60. This stress, it is that 25. So you just write that 25. 2 theta, theta is 30 times 2, that is 60. This is sine. Stress y is 45. Substitute by 45. Stress x is 75. Substitute by that 75. You get the answer. That answer plus that one will give you the resultant stress. The resultant stress. The resultant stress. Okay? Or you can also, maybe I can, this is the resultant for x prime, then also have the resultant for y prime, just in case. Then for that one, but most of the time we use this, but let me just do this one as well. So this time it will be stress y prime, you square it, you say plus, then you write the same thing again, x prime y prime, you square it. So both of them, we can just add both of them. Can just both of them right there. So you can calculate this or can calculate that one. With this too. Okay, yeah. So yeah, this is what we have. One last example. Now I'm going to do the last example and then we can go and sleep. It is 26. Let's do number 26, 1.26. 1.26 on those ones that we're doing. That is the last example for today, and then you can go and enjoy the sleep. Okay, so let's go ahead and do that. It says in a structural element, the stresses at a point in a material is shown in the image below. Then that is the image that they are showing us. Okay, let me just quickly throw it. Okay, you can take a screenshot of this before I take it out. And then we will go further. Okay. This is the last example. Okay, this is an element. You can see it is tensile. So stress Y is 25 megapascals. Then we have stress X, which is in this case compressive, and is equal to 30 MPa, megapascals. Then we have that for shear stress. So we have 15 megapascals. All right. There's no angle that has been mentioned in this particular case. So they are saying use the stress transformation formulae to calculate the principal stresses. Number one, they want the principal stresses. Okay. Then they are saying use the stress transformation formulae to calculate the principal stresses acting on the element and the position of the planes of which they occur. All right. So when they're saying and the position, they are referring to the angle. That means we should also find out at what angle is that. Okay. So that's what we will do. Now, what are the principal stresses? All right. The principal stresses, okay, I usually say before you set anything, first give us the values for a coordinates x and y. Let's start with x. So a coordinates is x, it will be this and that. So this is compressive, meaning it's negative. So negative 30. Now this is rotating, it's going up, that means it is rotating anti-clockwise, so it's positive. So it's about 15, that is positive, that is for x. I hope it makes sense. Then say y. For y, we have that being tensile, that means it is positive, so on 25 or positive. Then this is going in this direction, it's negative. Anyway, if this one is positive, this one has to be negative. They are always in opposite directions. So if you get this one right, you have to get this one right. So one is negative, one is positive, one is negative for the shear stress. So in this case, x is negative because it's compressive, y is positive because it is tensile. So this is what we have right there. Okay, then I can go and show you the answers. Firstly, when they are talking about the principal stresses, they are talking about stress 1 and stress 2. So these are principal stresses. I think man is a pen. Stress 1 and stress 2. So these are principal stresses. Usually, stress 1 goes with the bigger value, then stress 2 goes with a smaller value, but it will depend. Some people, they want to make stress 1 go with x, stress 2 go with y. It really doesn't really matter. So for me, I'll just say the bigger value is 1, the smaller value is 2. Okay, we can do that. So let's go ahead and see the formulas for stress 1 and stress 2. These are the formulas for this chapter. These are the formulas we have. They start from this line. Right under that line, below this line, we have these formulas. These ones is for the rotated values. Then this one also is for the rotated. Now, stress 1, this is the principal stress. Stress 2, this is the principal stress. So these are the principal stresses. So you will take those formulas to calculate, and you'll notice that they are the same except the sign there and there. This sign is positive, that sign is negative. That's the only difference. Otherwise, everything else is the same. Okay, so let's go ahead and put those formulas on the paper. So this is equal to stress x plus stress y over 2 plus then square root. One other thing I would like you to notice is that this square root, and this square root, and this square root are the same. 1, 2, 3, 4. Meaning that if you have this, you may ignore the square root and just use that value. And this is stress maximum, shear stress maximum, which is the same as the radius of a Morse circle, because that's the radius of the Morse circle. This is not resultant, it's radius. This R is for radius, not resultant, okay? The formula for your resultant stress is there in the previous page, in the previous example. So this R is for radius, not for resultant. I hope you do not confuse those two. Don't confuse it, even though R upper, this is for resultant, this is for radius, not resultant. The one for resultant, this is the formula for your resultant. This is the formula for your resultant. That's the formula for your resultant. All right. So as I was saying that you will notice that this, and this are exactly the same. All right. Okay. So let me write it. So it is the radius of the Morse circle, stress x minus stress y all over 2. Then you square it, everything squared, plus, then you have xy squared. Everything is under square root. Say that for this stress 2, let me write stress 2 here. Stress 2, the only difference is just that we have negative for it, plus stress y over 2, then minus square root. So there's stress x minus stress y over 2 squared plus shear stress xy, everything squared. So you just do these two, you get the answers. Those are the principal stresses, okay? These will be the principal stresses. So in the place of stress x, you will substitute by the value for stress x, which is 30 there. It's negative 30, in fact. So you'll substitute by minus 30 here. It will be negative 30. Then here it will be positive 25. Again, negative 30, positive 25. Negative 30, positive 25. Negative 30, positive 25. What about this one? This is that 15. Just write 15. You don't have to have plus or minus. Just write 15. So that is it. Then after that, you press the calculator, you get the answer. That's how you get those answers. All right. That is it. Then let's move to the next one. The next question. Oh, it says also and the position of the planes. Okay, when they are looking for the position, that means now they are looking for the angle. So what are we going to use to find the angle? Because they say that we must find the principal stresses, and then we should also find their planes. When it comes to angles, these are the formulas we are going to use. This is the formula we will use, in fact. This is for the angle. So we are going to use this. How are we going to use it? When you are dividing by a fraction, it is as though you are multiplying by its inverse, meaning that this 2 is multiplying there. So we have 2 times stress xy, shear stress xy, divided by stress x minus stress y. That's what I will write, because when you're dividing by a fraction, it's as though you're multiplying by its inverse. Okay, so that's what I'll write. So I'll say tan 2 theta is equal to 2 stress x y over stress x minus stress y. That's what I will write, and then you can do your substitution. So that means it will be 2 times 15 divided by negative 30 negative 25. Now this negative, it is because the formula is negative, otherwise 25 is positive, and then you'll get that answer. So this is how you get it. Now you can see it will come out negative, isn't it? Then after that, you can make now this the substitute of the formula. So we have 2x 2 theta equaling arctan of that answer. 2 times 15 over minus 30 minus 25. Then we get the answer, then we divide that by 2, therefore theta will equal to whatever value. So whatever value that you're getting here, when you press your calculator, you'll divide by that 2, and then you'll get the theta value. So this is how we will find that. And if it is negative, as you can see, we have negative values there, so probably the answer will be negative. If it's negative, that means it is rotating clockwise. If it's positive, that means it is rotating anti-clockwise. And that's it. That's it. That's how you solve for it and find the plane for it. Okay. Then after that, the next question says, draw more cell to verify your answer. Then they gave you the scale. Use the scale. 1 centimeter is equal to 5 megapascals. When it comes to drawing more cell, remember we have okay, let me just go ahead and draw it. One is negative, the other is positive. So we will have our line on both sides. Okay. So remember I said that we have positive on this side. We have positive on that side for stress, for shear stress, positive is underneath. Okay, then you will just do your marking according to his scale. It really doesn't matter. Then I'll just mark tens. So I'll say 10, 20, 30, 40, and so on. Okay, 10, 20, 30, 10, 20, 30, yeah, and so on. I will 10, 20, 30, 40, and so on. These are the negative values. So this is minus 10, minus 20, minus 30, minus 40. And so in the upper is minus values, positive values. Now we have 15. So this is positive 15, and that is negative 15. Then because that is the shear part, x is negative because it's compressive. So x will be on this side as minus 30. There is minus 30. That minus 30 goes with positive 15. So meaning this is what we have. Then on the other side, we have 25. Y is 25. So this is 20. This is 10. This is 20. 25 upaya then 25 goes with 15. They are meeting there. Since they are meeting here, then you're going to join those two. When you join them, you'll get a center somewhere there. So let's join them. Sometimes so that is the center. So this is 0. Now they are very close to each other. Then this will be the maximum and the minimum shear stress. This line is for a maximum and minimum shear stress. Okay, so you will use your compass to actually construct the circle and draw it. Constructing a circle now. You will draw it the way you'll draw it, and then you'll get the values that you need to get. Then for those values, now this part where this circle is touching, this part, since this is from is the bigger value for me, I will say that is stress 1. Remember I said for me, I'll use stress 1 as the bigger value, then stress 2 as the smaller value. So that will be stress 2. So that's how you will do it. Now, some of the times they will want you, in other words, and stress 2, there will be these values. Because they say we must prove. There will be these values. If I selected them wrongly here, that means I will put stress 1 in the place of stress 2. That's all it means. So we can do that. Then after that, we will have to check the angle. This angle, we have to measure it. Now, when we are measuring it, how are we going to measure it? We will measure it from here to there. That will be the angle we are going to use, or from there to there, it really doesn't matter. So we are going to measure, it should be 2 times theta. In other words, if here we get 10 degrees, here we should get 20 degrees. Because this is 2 times theta. So if this is 10, this should be 20. You are going to measure it, so it will come out through your measurement. Okay? And then you'll prove that this angle and these values are the same. That's all you need to do. So you need to find these stresses, stress 1 and stress 2, and then you need to find this angle, because that's what was asked in the previous question. So that's how to use Mossel to verify the answers that you got from that. Sorry, this isn't always the case whereby you should flip the y-axis. Yeah, it's always the case. It's always the case. So the y, that is why we have positive underneath. It's always the case for this one. Usually positive y bangentla, but this time positive, or yeah, I think that's what you mean by flip. I'm not sure. I think that's what you mean by flip. Or if maybe that's not, you can clarify what you mean by flip. But about to throw up, yes, you flip it that way. Okay, sure, yeah. So that is it, guys. That is it. This is the last example. I hope it makes sense. If you have more questions, I'll be able to, namhlanje still I'll have some time for the last time, then I'll be busy there starting from tomorrow. So namhlanje, sorry, even on Thursday, it's not yet 12 p.m. Even on Thursday, I will have some time to answer questions. So you can send your questions. I will be able to answer them during the day and also sometime at night. But I will sleep a little bit early because I'll be preparing to work Friday. Okay, so I won't be available Friday. Okay. Tomorrow at any time you can talk to me at any time tomorrow. I'm not going to have a class. I'll just have to answer questions. If you have questions, I will answer them. Not necessarily a class, but I will answer them. Then if I have a class tomorrow, it will be from 11 a.m. 11, maybe 11 to 12, maybe to explain a few things. Okay. After that, I will also touch up on the last module, which is cranes. For cranes, I will not really. How am I gonna do it? I'll see how am I gonna do it. But what for this one is always following. It's just about following these steps. For example, this page 300 in your textbook. It's mostly always about following these steps. But maybe I will do one example with you tomorrow, and especially the ones for derrick cranes, because the one for shear legs, they are quite easy, very easy, but the one for derrick crane is a little bit complex. So I will do one example with you for derrick cranes. Derrick cranes, they are divided into three types. Derrick cranes into three types. We have the ones that we have angle that we have a type of bisecting the legs. Then we have another one that is along one leg, the other one that is at an angle. So I'll do one of those, but I'll show you their differences. I'll just show you their differences. It's not that hard, but yeah, it needs some focus. So I'll do one of them. Okay, let's meet again tomorrow by 11 a.m. 11 a.m. I will have another live then where I will do one example with the derrick cranes, forces and structural frameworks. So I'll do one example with derrick cranes tomorrow. Okay, that's it for today. See you tomorrow. Unless there's a question, I'll just wait for a few minutes to check if are there any questions. So tomorrow we'll do derrick crane, just one example. Got 11 a.m. I'll do it. If there are no questions, see you tomorrow, guys. Bye-bye.